In this talk, I will talk about the fine-grained complexity of parity problems with Amir Abboud and Oren Weimann, and my name is Shon. So I want to start by showing how to use fine-grained complexity to obtain conditional lower bounds. We start with a popular conjecture that says that some problem x cannot be solved in time better than n to the delta, up to improvement in the exponent. Then we reduce that problem x to your problem in time better than n to the delta, again up to improvement in the exponent. Then conditioned on the hardness of that problem x, your problem cannot be solved in time better than n to the delta. Now I want to give examples for problems that are used as hardness conjectures. And the first one is all pair shortest path, in short APSP. The input for the problem is an edge-weighted graph, and the output is to return the distance between every two vertices. There is no known subcubic algorithm for this problem, and it is conjectured that such algorithm does not exist. A related problem is the negative weight triangle, which gets us an input, an edge-weighted graph, and the output is to return if there is a triangle in the graph such that the sum of the weights on the edges of the triangle is negative. It is known that negative weight triangle can be solved in subcubic time if and only if all pair shortest path can be solved in subcubic time, and we call such problems subcubic equivalent. Another problem that is used as a hardness conjecture is the free-sum problem that gets us an input, a list of n integers, and the output is to return if there are free numbers in the list that sum up to 0. There is no known subquadratic algorithm for the problem, and it is conjectured that such algorithm does not exist. Another problem is mean plus convolution that gets us an input, two lists a, b of n integers, and the output is to return a vector c where ck equals the minimum of ai plus bj, where I plus j equals k. There is no known subquadratic algorithm for the problem, and it is known that if all pair shortest path can be solved in subcubic time, or free-sum can be solved in subquadratic time, then mean plus convolution can be solved in subquadratic time. So the hardness of mean plus convolution implies the hardness of all pair shortest path and the hardness of free-sum. Here are some known results in fine-grained complexity, and there are many problems that are subcubic equivalent to all pair shortest path, such as negative weight triangle, mean plus product, radius of a graph, median of a graph, maximum two-dimensional subarray, metricity testing, Wiener index, second shortest path, and more. So if one of these problems has a subcubic algorithm, then all of these problems have a subcubic algorithm. Also, there are problems that are subquadratic equivalent to mean plus convolution. Subquadratic equivalent is the same as subcubic equivalent, but with exponent 2 instead of 3. A few of these problems are 0-1 Knapsack, maximum consecutive subsums, and approximation of subset sums. Also, under the free-sum conjecture, there are conditional lower bounds for problems in computational geometry, dynamic problems, and more. So now let's have a look at our results. And we consider the parity versions of classical problems studied in fine-grained complexity. And we have two types. The first type is parity computation that asks if the solution for a problem is even or odd. So for example, instead of computing the diameter, you can compute the diameter parity, which asks to return whether the diameter is even or odd. The second class is parity counting that asks if the number of solution is even or odd. And we can consider the problem of negative weight triangle counting that asks to count the number of negative triangles in the graph. And the negative weight triangle parity asks to return whether the number of negative triangles in the graph is even or odd. In the paper, we show that for many classical problems, finding the exact solution is as hard as finding its parity. So here we have a table of our results in bold, and this is the all pair shortest path related result. So first we show that all pair shortest path parity is subcubic equivalent to all pair shortest path, where all pair shortest path parity is computing the parity of the distance between every two vertices. We also have the median problem, which is subcubic equivalent to all pair shortest path, and in the paper we show that median parity is subcubic equivalent to all pair shortest path and median itself. Similarly, we show that radius parity is subcubic equivalent to all pair shortest path and radius itself. We show that sum of eccentricities is subcubic equivalent to all pair shortest path, and also that computing the parity of the sum of eccentricities is subcubic equivalent to all pair shortest path. There is also the integer betweenness centrality problem, which is known to be subcubic equivalent to all pair shortest path, and also that approximation of integer betweenness centrality is subcubic equivalent to diameter. In the paper, we show that integer betweenness centrality parity is subcubic equivalent to all pair shortest path. We also show that computing the parity of the second shortest path is subcubic equivalent to all pair shortest path, and that computing the parity of the Wiener index is subcubic equivalent to all pair shortest path, where the Wiener index is the sum of all the distances between every two vertices in the graph. We have more similar results of problems that have their parity version subcubic equivalent to all pair shortest path and themselves. We also have results that are not related to all pair shortest path. So for example, we show that diameter parity is subcubic equivalent to diameter itself. We also show that mean plus convolution parity is subquadratic equivalent to mean plus convolution. We also show that 0,1 knapsack parity is subquadratic equivalent to mean plus convolution and itself, and that ridge centrality parity is subcubic equivalent to diameter. So now I want to talk about one of the reductions from the paper, and we will later see how it is used. So we consider the problem negative triangle vertex parity, in short NTVP. The input for the problem is an edge-weighted graph, and the output is the parity of the number of vertices belonging to a negative triangle. So just so we will see what it means, here we have a graph, and we can see that this triangle is negative because the sum of the weights on the edges here is negative. Also, this is a negative triangle, and this is a negative triangle as well, and those are all the negative triangles in the graph. And here we have all the vertices in a negative triangle marked in red, and we can see that we have 6 vertices marked, and therefore the negative triangle vertex parity of this graph is 0 even. So now I want to present the reduction from negative weight triangle to negative triangle vertex parity, and we start by choosing a subset of vertices randomly and uniformly, V1. So here we have the set of vertices that we selected, marked in green. Next, for every vertex in V1, we create a copy vertex, V2. So here we have the copied vertices, marked in orange. Next, for every edge that has its 2 endpoints in V1, we copy it to V2. So here we have the copied edges. Next, we define V complement to be all the vertices in the original graph that are not in V1, and we mark them in blue. Then for every edge U1V, we add the edge U2V, where U1 is in V1, U2 is the copy of U1 and V is in V complement. So here we have the edges, and this is the final graph of the reduction, which we call G prime. Notice that a vertex in V1 is in a negative triangle if and only if its copy vertex is in a negative triangle as well. Therefore, V1 and V2 together add an even amount of vertices in a negative triangle to negative triangle vertex parity, and therefore the vertices in V1 and V2 do not affect the negative triangle vertex parity of G prime. Also notice that a vertex in V complement is in a negative triangle in G prime if and only if it was in a negative triangle in the original graph. So we get that the negative triangle vertex parity of G prime is the negative triangle vertex parity of all vertices in V complement. So if G has a negative triangle, then with probability half we select an even number of vertices in a negative triangle to V complement. Therefore, with probability half, the negative triangle vertex parity of G prime is 0. On the other hand, if G does not have a negative triangle, then also G prime does not have a negative triangle. So with probability 1, we get that the negative triangle vertex parity of G prime is 0. And this completes the reduction. So we have a reduction from negative weight triangle to negative triangle vertex parity, and therefore we have a reduction from all pair shortest path to negative triangle vertex parity. And in the paper we show reductions from negative triangle vertex parity to other problems such as integer betweenness centrality parity and Wiener index parity. Notice that there are reductions from these problems to all pair shortest path, and therefore we obtain that all of these problems are subcubic equivalent. So now let's discuss a more natural parity version of negative weight triangle, which is the parity of the number of negative triangles in the graph. It is known that counting up to n to the 2.99 negative triangles is subcubic equivalent to all pair shortest path, and also that approximate counting of negative triangles is also subcubic equivalent to all pair shortest path. This raises the question whether negative triangle counting is subcubic equivalent to all pair shortest path. Perhaps we can show that parity counting is subcubic equivalent to all pair shortest path. And to address this question, we consider the problem zero-weight triangle, which gets us an input, an edge-weighted graph, and the output is to return whether there is a triangle in a graph with total zero weight. There are reductions from threesome to zero-weight triangle, and also from all pair shortest path to zero-weight triangle. So solving zero-weight triangle in subcubic time implies a breakthrough because it implies better algorithms for threesome and all pair shortest path. Also, reducing zero-weight triangle to negative weight triangle would imply a breakthrough because it would imply that all pair shortest path is threesome hard, which is not known to be true. So we get the intuition that zero-weight triangle is generally harder than negative weight triangle. But here we show that counting zero-weight triangles reduces to counting negative weight triangles, and also that parity counting zero-weight triangles reduces to parity counting negative weight triangles. We now prove the first claim. The proof of the second claim is similar, and the proof is actually very simple. First, compute the number of triangles in the graph in the time it takes to multiply two matrices, which is subcubic. Then compute the number of negative triangles using a negative weight triangle counting algorithm. Then use the negative weight triangle counting algorithm to compute the number of positive triangles by negating the weights in the graph. Then every positive triangle turns into a negative triangle. Finally, we compute the number of zero-weight triangles by taking the number of triangles and removing from it the number of negative triangles and positive triangles, and this completes the proof. So counting negative weight triangles is conditionally harder than negative weight triangles because a reduction from counting negative weight triangles to negative weight triangles would imply that all per shortest path is free-sum hard. In the paper, we show a reduction from zero-weight triangle to zero-weight triangle parity counting, so conditionally there is also no reduction from negative weight triangle parity to negative weight triangle. So now we consider the mean plus convolution class, and I remind you that mean plus convolution gets us an input to lists A, B of n integers, and the output is to return a list C where Ck equals the minimum of Ai plus Bj, where I plus j equals k. There is also the knapsack problem, which gets as an input n items. Each item has a weight and a value, and also the problem gets a target weight t. And the output is to return the maximum value you can get by selecting a subset of items from the knapsack, with the constraint that the sum of the weights is at most t. Another problem is the super-additivity problem, which gets us an input, a list of n integers, and the output is to check that for every ij, ai plus aj is at most ai plus j. And it is known that all of these problems are subquadratic equivalent. So now I want to show that Knapsack is subquadratic equivalent to Knapsack parity and mean plus convolution. And the proof goes by modifying the original reduction from super-additivity to Knapsack. And I remind you that super-additivity asks to check whether for every ij, ai plus aj is at most ai plus j. And we set first every ai to ai plus w times I, where w is a large enough value. So we get that the list is monotonically increasing and a0 is 0. So now we need to create the knapsack instance, and to do this we need to specify the item in the knapsack. And we have two types of items. The first is type A. So for every I, we create an item with weight I and value 2 times AI. And we have type B items, such that for every I that is not 1, we create an item with weight 2n minus 1 minus I and value 2 times W minus AI, where W is a large enough value. For the case of I equals 1, we increase the value of the item by 1. Also, we set the target weight t to be 2n minus 1, so every solution that gets a weight larger than 2n minus 1 is not a valid solution. Notice that there is a possible solution for this problem that takes the type A item for I equals 1 and the type B item for I equals 1. This solution has weight of exactly 2n minus 1 and value of 2w plus 1. So every optimal solution must have value of at least 2w plus 1. What we want to show is that A is super-additive if and only if the solution for this knapsack instance is odd. We want to show first that the optimal solution has exactly one type B item. This is because if we have 0 type B items, then the maximum value we can get is by taking all of the type A items, and the value would be at most the sum of 2 times AI for every I. but this is smaller than 2 times W, where W is a big enough value. So this case is not optimal. If we have 2 type B items, then we get that the weight is more than 2n-1 because the weight of each item is at least n, and therefore this case is disqualified as well. So now let's consider the case where A is super-additive, and we want to show that if A is super-additive, then the knapsack solution is odd. So if A is super-additive, then the optimal solution has exactly one type A item, because if we have 2 type A items with indices I and j, we can replace both of these items with one type A item with index I plus j. So the weight remains I plus j, but the value is not decreased because of the super-additivity, because 2 times AI plus 2 times AJ is not more than 2 times AI plus j. So we get that the optimal solution has exactly one type A item and exactly one type B item, and because the list is monotonically increasing, then we must have that both of these items have the same index, k, and this solution has weight of exactly 2n-1, and it has value of 2w. Unless k equals 1, then we add 1 to the solution, and we get the solution from the beginning with value 2 times w plus 1, and this solution is optimal and odd. So now we want to show that if A is not super-additive, then the knapsack solution must be even. If A is not super-additive, then there are some I and j such that AI plus AJ is greater than AI plus j, and there is a solution with a value larger than 2w plus 1 by selecting the items for I and j for type A items, and also taking the type B item for index I plus j. So we get a solution with weight 2n-1, and by the violation of the super-additivity, we get a solution with value which is larger than 2w plus 1. And we know that if we use type B item for I equals 1, then we get that the maximum value is 2w plus 1, as we have shown before. And therefore, the optimal solution does not use the type B item for I equals 1. And we get that the optimal solution must be even because this item is the only item that has an odd value. So that's it. In the paper we show that many problems are equivalent to their parity version, and thanks for listening.